Let's delve into the world of Turing machine configurations. This presentation will cover instantaneous descriptions and computation sequences. It is important to understand how Turing machines represent their current state and execute computations. This is the foundation for understanding more complex operations. So, what exactly is a configuration in the context of a Turing machine? A configuration, also known as an instantaneous description, captures the complete state of a Turing machine at any given moment during computation. Think of it as a snapshot of the machine's status. A configuration consists of three key components: the current state, which is the machine's present control state, the tape contents, which includes all symbols written on the tape, and the head position, which is the location of the read or write head. Let's talk about how we represent a configuration using a specific notation. We use the notation alpha, q, beta, where alpha equals the left part of the tape, representing all the symbols to the left of the read or write head. Q represents the current state of the machine, indicating the state the machine is currently in. Beta equals the right part of the tape, which includes the symbol at the current head position, as well as all symbols to the right of it. Let's illustrate the configuration notation with an example. Imagine we have a tape with the following contents: a blank symbol followed by 10110, and then another blank symbol. The read or write head is currently positioned over the first one. In our notation, this configuration can be represented as 10Q2110. Here, 10 represents the part of the tape to the left of the head. Q2 is the current state of the Turing machine, and 110 represents the part of the tape starting from the head position to the right. Now let's discuss computation sequences. A computation sequence is a series of configurations. It shows how a Turing machine transitions from one state to another during its execution. Key characteristics of computation sequences are that they are sequential, which means each configuration follows from the previous one. They are deterministic, where transitions follow the defined rules of the machine, and they are complete, showing the entire computation process from start to finish. Each step in a computation sequence represents a transition from one configuration to the next. We denote this transition using the notation C1 yields C2, where C1 is a configuration that yields C2. This notation means that the machine reads the current symbol under the head, applies the transition function delta of Q and A, which involves updating the state, writing a symbol, and moving the read or write head. This results in a new configuration C2. Let's walk through a computation example to see how these transitions work in practice. We start with the configuration blank symbol Q0101 blank symbol. This transitions to 1Q101 blank symbol. Then it transitions to 10Q21 blank symbol. This sequence shows how the Turing machine moves from the initial state and tape content through a series of steps, updating its state and head position according to its transition function. Here are the key takeaways from this discussion. Configurations capture the complete state of a Turing machine at any moment during computation, and computation sequences show how the machine transitions through states, using notation C1 yields C2. Understanding these concepts is essential for analyzing and designing Turing machines. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.